Hello everyone. Today we're talking about some predictive insights about the Melbourne housing market. The Melbourne housing market offers a dynamic landscape for analysis, shaping economic decisions and urban planning globally. Understanding such market is pivotal. Our project delves into the vibrant Melbourne market, aiming to uncover key insights that inform stakeholders, from investors to policymakers, facilitating informed decision making. Our selected dataset comprises 22 variables covering various aspects of properties sold in Melbourne, providing a robust foundation for analysis. These variables, including location, property type, size, and room count, offer a comprehensive view of the market dynamics. Through descriptive statistics, inferential analysis, and predictive modeling, we aim to focus property price trends and gain a nuanced understanding of market drivers. Rigorous data cleaning and preprocessing ensure the integrity of our findings by addressing missing values, outliers, and inconsistencies, ensuring reliable insights. The dataset initially contained numerous missing NA and infinite value across several variables. Analysis revealed more than 7,000 missing entries in the price variable, which were subsequently removed. Among other variables such as year built, land size, car, bathroom, bedroom, latitude, and longitude, varying degrees of missing values were observed. Notably, over half the data for year built was missing, leading to its exclusion from further analysis. For variables such like uh, car, bathroom, and bedroom, which denote the number of cars that can be accommodated and the number of bathrooms and bedrooms in a house respectively, we replace missing value with zero, and presuming the absence of these features. However, substituting zero for missing land size value seemed inappropriate due to its quantitative nature. Instead, we imputed these missing values with the mean of the available land size data to maintain analytical integrity. There are still some missing values in the variables latitude and longitude. However, these variables may be related to another variable postcode, since all represent the location of the house. Therefore, conducting a linear regression to explore how these factors relate to the response variable price is essential. As shown in table, the R-square value is significantly lower than postcode is omitted, and it remains approximately the same when latitude and longitude are omitted. Based on these findings, we have decided to exclude latitude and longitude from our analysis. Outliers in data analysis can skew statistical results, impacting interpretations. To address this, we examined the distribution of price using a histogram, revealing a right-skew distribution. Applying a natural logarithm transformation clarify the visualization and reduce skewness, making outlier identification easier. This transformation notably decreased the impact of outliers, enhancing the reliability of our analysis. We noticed several variables, including distance, postcode, building area, and property count, were incorrectly formatted as characters. Converting these variables to numeric is crucial for easier model building and interpretation, reducing computational complexity and enhancing accuracy. Additionally, nominal variables like type, method, region name, parking area, and date represent categories without inherent order. For instance, we simplify the date variable into 7 values representing different days of the week, streamlining data processing for improved analysis.
Okay, I will show how we use linear regression to build a predictive model. The model's formula shows there. So to measure how well the model works, we use two metrics. The R-square, which shows how much of the data can be explained by the model, and the root mean square error, which tells us how far of your predictions are from reality. The training data root mean square error was 415,000, and for the test data, it was 458,000. So the R-square values were similar across the both datasets. So despite the numbers being close, the model wasn't perfect because we had too many variables here. We are now exploring the PCA to simplify the model and improve accuracy by reducing the number of variables. So the PCA helps to reduce the number of variables in the dataset while retaining as much information as possible. Our team used PCA to transform the original variables into principal components, the first few of which capture most of the variation. We standardize the data and then calculate the covariance matrix to understand how variables relate to each other. We selected the top eigenvectors to create a matrix and use it to transform a dataset into fewer dimensions. With PCA, the first 22 principal components captured nearly 80% of the variance. We then rebuilt the linear regression model, and all metrics improved. You can say the training root mean square error dropped to 332,000 with an R square of 0.754. And the test root mean square error was also dropped with an R square of 0.742.
So our next step is XGBoost. Without standardizing or normalizing the feature, we directly fit the model using extreme gradient boosting, a decision tree based ensemble machine learning method. So the objective function here includes both a predicted loss and a regularization term that penalize the model complexity. So the main goal here is to minimize the loss as small as possible. So our team trained the model over 100 boosting rounds and ensured robustness and generalization by conducting a tenfold cross-validation. The model performance was evaluated using the following matrices here. And also, we also conducted the feature importance here, which we will explain later. But the data here seems a little strange. The model fits extremely well. So that's might be a sign of overfitting. And then, so following the initial modeling phase, we focus on dimensionality reduction to simplify the model and to enhance the generability. So here we combine XGBoost and PCA together. Instead of utilizing all original data here, we train the XGBoost model on principal components, which are selected before based on their ability to capture the maximum variance in the data. As the data here shows, it looks better than the previous ones. And to further enhance the model's robustness, particularly in generalization to the unseen data, we implemented regularization techniques. So for L1 and L2, we both use it, and they drive some coefficients to zero and automatically selecting the features when using L1 regularization. And for L2, they will shrink the coefficients, but not directly necessarily drive them to zero. Through this method, the model perform better than the previous tools, which demonstrating their efficiency, enhancing the predictive stability and accuracy of the model. And from both R squares, they are reasonable here. So let's derive the top 5 price driver, which is our goal to find their price driver. And so from all of the models, we listed all the top 5 factors here. So the result consistently highlighted the critical importance of a property's location, as here we can see either they are located near political locations or they are in the city, as well as the size in terms of room count. And these findings align with the well-known real estate valuation principles. And so from all of the methods and experiments we had and all the findings we had, so the most recommended method is to use XGBoost with regularization and PCA. And also for different roles, we have different suggestions here. For investors, we will suggest to mainly focus on the price drivers. And for policymakers, we will suggest them to implement the target policies in emerging areas to enhance the property values. So that's the end of our presentation, and thanks.